Okay, so I'm here to talk about anti-entropy, which is the process where we've got data distributed across many servers, and how do we make sure that the data that's on one server matches the data that on another server quickly and efficiently, and how do we find the gaps quickly and efficiently if there are such gaps between those things. And I've been working for the last 6 months on an Erlang anti-entropy library for doing this. And it's a general library, but it's mainly targeted at the Riak database. So I'll tell you a bit about why I'm doing that. I work for the National Health Service in England. So good news, we've got 2 National Health Services, I think, presenting at CodeBeam today. So in England, we have a Riak installation. So I'll tell you a little bit about why we have a Riak installation, why we need anti-entropy, and why we've now decided we need better anti-entropy than we've got in Riak at present. For those who aren't familiar with Riak, it's a distributed key value store that was originally written by a company called BEAM STO. That company went out of business. Fortunately, all the assets were bought up by Bet365, who are one of the major customers of BEAM STO, and then they open sourced it all. Was that about a year ago, Brian? Yeah, so we're only on our first birthday roundabout rather than our 20th birthday for being fully open source. And now it's run by the community, and that's part funded by the NHS, who have a big installation. And in April of this year, we got our first community release of Riak out, so Riak 2.2.5 came out, and we're now working on Riak 3.0, and the anti-entropy work is very much part of that. Okay, so the system in the NHS that uses Riak is a system called Spine Core, and this is a system that's a back-end to many, many applications around the National Health Service, particularly in primary care. It stores a large amount of data, about 2 billion records and documents. It supports lots of different transactional messages of different degrees of complexity, and we get a large number of requests per day. And on this system, what we really care about are availability, durability, and reduced variation in response time. So unlike with the sort of WhatsApp database, if you heard about that yesterday, where they really cared about sub-microsecond response times, they're not important to us, sub-microsecond response times. But what is important to us is that if we give a 20 millisecond response time one day, is we keep giving a 20 millisecond response time the next day, and applications that depend on it can rely on that response time, and it doesn't suddenly become 200, 500 milliseconds. But we really care about availability. We don't really know what would happen if the spine went down and what would fail. We don't really control our customers and the applications, what the knock-on effects are. It may well be there'll be people queuing for prescriptions and all this kind of stuff, and there could be some political impact. And we really care about durability. There's both political and pragmatic sensitivity around what would happen if we lose data. So it's very important that we don't lose data and we're always available to our users. So in 2003, the first version of Spine was kind of conceived and built, and they needed a back end for that, so they went out to a large-scale enterprise database, and so they got a big load of Oracle instances, and they got a big storage system from Sun, and in theory, this was going to solve all our problems of durability and availability. And so it was good because we had dual sites for availability. Unfortunately, it took about 4 hours and an army of people to manage the process of failing over between the sites, so no one ever wanted to do the failover, so it wasn't really that available. And we had lots of resilience in these black boxes, these mystery black boxes. They all had duplicate components and this kind of stuff, and so we were told by the vendors of the boxes that they would never fail. But unfortunately, all those duplicate components just found weird and interesting ways to coincide failures and race conditions and this kind of stuff. And so they just developed failures that no one understood. And we had dual sites for durability. So everything that was written to one site got replicated over to the other site. So that was good, and someone said, well, that's great, because if a plane lands on the data center, we won't have any ACT transactions that aren't on the other site. And that's good for planes landing on data centers, not obviously good for the passengers of the planes, but good for handling that scenario. But that scenario is very rare, and what's more common scenario is data centers get partitioned from each other, or a data center goes dark because the power's gone off and this kind of stuff. And in that scenario, we still have availability because we've got a data center left, but we don't have durability anymore because we have nowhere to replicate the data to. And all this data had to be replicated synchronously for safety, because we're dependent in this database on keeping this transaction log in sequence and this kind of stuff. We can't fail over before some transactions have got over, because then those transactions will never be able to be played in the future. So that gave us some safety principles and some strong consistency, but unfortunately it meant that all our transactions were subject to the latency of the delay between the sites, and the impact of that latency was unpredictable, and the feedback from that led to variation in latency. So in theory we had durability, in theory we had availability, in theory we had reduced variation. In practice was a very different story. So we had to do something different about that, so Oracle came in, Sun came in, many thousands of man-years of effort went into thinking about this problem and what we could do, and then there was a huge transition that cost a load of money, and in 2008 we had a new solution from Oracle and Sun, which looked pretty much the same. I mean, it is subtly different, I promise you, but by and large, all the problems that we had before, we'd made slightly improvements on those problems, but fundamentally they still existed. So that wasn't much good. As we move forward into this decade, we had to decide what are we going to do next with this. And obviously, Oracle sales staff came back in again, and the consensus within the organization, 99% of the people talked to that Oracle sales staff and said, well, you know what we can do now? We can buy, they've told us what we didn't need was that crappy old computer they sold us. They can sell us a much faster computer now, and that will solve all our problems. So everyone thought, well, this is great. We can run this on a supercluster now. It's got super in its name. How can that possibly go wrong? So 99% of the people wanted to do that, and me and about 1% of the people said no. We must find some other way of doing this. And it's a very long story about what happened, but eventually the 1% won, and we agreed to do something differently. So in 2014, we had a new spine core. So at the top, we had some new, we rewrote the whole application, and we rewrote it on some new principles. We had asynchronous message passing between actors. We had supervisors restarting failed processes. We had some standardization of behaviors of our actors and this kind of stuff. And as an application, that worked really well. And at the back end, we now had a new database, and we'd chosen the Riak store for doing that. And the reason for choosing the Riak store is what we found is that as nodes failed or sites failed, we still kept maintaining the guarantees of durability and availability. So data was always copied to 2 separate physical nodes before we act everything back. It was eventually copied to 6 nodes, and we could fail things, we could fail sites, we could disconnect sites, and that would still eventually occur. We'd still eventually get the data in all 6 places, and we still immediately get the data into 2 places. And we didn't have to compromise durability to get availability, or compromise availability to get durability. We no longer needed synchronous replication between the sites because we were replicating first within the site. So, in theory, our plane landed on the data center. We would lose some amount of data, but in actually the likely disaster scenarios, we weren't going to lose data, and we're going to maintain availability. So that was a good compromise for us. So this has worked out much better. And the kind of high-level changes that we got out of using Riak KV. So the first big one is in hardware maintenance costs. So in the old system, we had very expensive proprietary hardware. Everything had to be on 4-hour fixed times. Everything needed specialist people on call to support it and this kind of stuff. Now we've got this simple Erlang-based key value store running on commodity hardware. And if something fails, we don't have to fix it straight away, because something else could fail and it would still keep running. And that time that we can give to fixing things and the fewer people that we need to support it means that we had around about a 98% reduction in our hardware maintenance charges. And the fear of failover has gone away, so it's no longer a 4-hour process to fail over. It's an instant process, so we always fail over when it's necessary. We don't pause because we try and fix it where it is, because we don't want to take a 4-hour outage because we started the failover process. And as a consequence now, over the 4 years now that it's been live, we have maintained 5 nines availability over 24/7. And we've done this with effectively only one engineer on call at any one moment in time. So we've gone from having 20 to 30 people on call to just having one person on call for the whole system. So for us, we've had great benefits from that. So, as a consequence, the NHS really wants to stick with Riak going forward, despite Basho not being around. So with Riak, we're now distributing the data into many places, and that data is going to be eventually consistent. So we need some tools to help us with that, and Riak provides some tools. It provides these things called dotted version vectors, so we can actually track causality, and we make sure we don't have race conditions, so we don't have data loss because of last right wins or anything like that. We have hinted handoffs, so if a vNode takes over from a primary vNode because a primary vNode is not down, when that vNode comes back up, it will hand off all the data that it received in the interim. We have read repair, so every time we read within a cluster, it checks all the places it should be within the cluster, and even after we return the result to the client, it will go and repair any out-of-date data. We have a real-time replication push, which has some queuing in and this kind of stuff to make sure that if we get temporary network failures, we still get the data across in real time. And then we have this kind of full sync process. So we've got 2 clusters. We want to check that the 2 things are consistent. Well, there has a way of doing that. And in effect, what it does for each vNode, and we have like 128 vNodes within our database cluster, it rolls over them one by one, folding over all the keys and objects, creating a sorted log of keys and hashes, does that on the vNode on the other side, compares the sorted logs, gets a set of keys and hashes that are different, and then works out what needs to be changed and repaired. So so that gives us some tools for helping with this, but there's some drawbacks to these tools. The first drawback is that per vNode key listing is extremely expensive. We don't have really a long out-of-hours period, a long quiet period to run it in. It has substantial costs, and it was dominating the costs of running the service. And eventually, we actually had to turn it off and use some kind of slightly hacky, slightly less reliable mechanisms of confirming our clusters were in sync. The other problem is that when we're doing gets, is that we're going to read from 3 places within the cluster, and we're always going to make sure we've got the most up-to-date data. But also sometimes we have to do queries that go across a coverage set of vNodes, and in that case, for each record, we're only reading from 1 place. And so we're not validating that we got the most up-to-date version. And so really what we want is something behind the scenes that's making sure that all the data's got to all those 3 places, so that when we run those coverage queries, we're actually going to get the right results. We can deal with, in the short term, immediately after an update, not immediately getting the right results, but sometime after we want to make sure that we are getting the right results. So we need something to resolve these problems. And the answer to that in Riak was active anti-entropy, and this got released in 1.3 of Riak. Active anti-entropy is based on a thing called Merkle Trees. So what are Merkle Trees? Well, Merkle Trees, I think, have been around since the 70s. I think they were patented by Ralph Merkle in 1979. They've recently gained some more popularity because they're used within blockchain as a way of confirming the validity of blocks. In Riak, Merkle trees are used as a simple hash tree. So this hash tree that's drawn up is 2 deep and 4 wide. In Riak, they're 2 deep and 1,024 wide. So at the top, we've got a root node. Below the root node, we have 1,024 branches, and beneath all 1,024 branches, we've got 1,024 leaves. And those individual leaves, those sort of million leaves, we call segments, okay? If we've got a key in our key value store, we're going to hash the key to one of those 1 million segment IDs, okay? And that key lives under that segment. And that segment ID has a hash. And that hash is a representation of all the keys and hashes that live under that segment, okay? If we then take all the hashes, all the 1024 hashes under a branch, we can produce another hash from that, and that represents the hash of that branch. And if we take all 1024 branch hashes, we can provide another hash of that at the top, which is our root hash. Now, if we have two lots of data that are the same, they will have the same root hashes. So in order to confirm that these two databases in a Merkle tree format are the same, we simply have to compare those two roots. So we have to compare two, like 8-byte hashes or whatever they are. Okay, so that gives a very quick way of confirming. If we find that the root hash is different, we can look and see, well, which branch hashes are different. And then we can look and see which leaf hashes are different. And we can very quickly locate whereabouts in the tree in which segments are there differences in the database. And then we only need to repair those segments. Okay, so these Merkle trees, these hash trees, give us a nice building block for efficiently comparing very large data stores. So in Riak, how does that kind of work? Well, we have all these different vnodes, and those vnodes, each vnode will have an attached hash tree process. And when we get a change into a vnode, we pass the new record over to that hash tree process. And the hash tree process can look at the key and work out which segment it belongs to. And what it then says, it says to its hash tree, that segment is now dirty. Okay, so you're going to have to recalculate that sometime in the future. And then in the future, when it needs to do an exchange, it goes and looks at what its dirty segments are, and it goes and says, all right, for each of those dirty segments, I need to find all the keys and hashes under that segment. I need to recalculate those segment hashes, and then recalculate all the way above the tree. It can then do an exchange, and when it's done an exchange, if we've found differences, we've got a set of segment IDs back, and it now needs to do the reverse. It now needs to go from those segment IDs and work out what all the keys and hashes are that sit under that segment, so it can compare the actual keys and work out which keys are out of sync. So for both mismatched segments and dirty segments, we need to go and search and find keys and hashes by segments. So one of the downsides of this, in order to maintain an active entropy tree where we can't keep all the keys and hashes in memory, we need to keep a separate key store, and that separate key store needs to be segment ordered so we can efficiently do these segment queries. So we actually use a key ordered store, but then we insert into the front of the key the segment ID, and we've got a segment ordered store, and we can do the folds efficiently to handle both dirty segments and mismatched segments. So this is how active entropy works in Riak at the moment, and this has some mysteries, has some issues. The key store has a memory cost. Yeah, because we have to, the store ultimately ends up being cached in memory, even when we can't hold it in memory, or most of it does, and it steals memory from other things that we would like to give memory to. Periodically, though, as well, is that we've now got a key store that's separate to our actual vnode database. And we may well lose some data off disk from that vnode database. We may have a corruption or some other kind of failure. We don't want to keep exchanging the valid information and saying, oh, we've got all that data. We need some way of making sure that the key store keeps up to date with the database store. So periodically, we trash the key store and rebuild it again from scratch from the database store. But that has an unpredictable impact on performance. We can control that unpredictable impact by slowing it down, by throttling the process of rebuilding that store. But when we slow it down and throttle it, the consequence of that is that we have to spend longer without an AE exchange because we don't have a valid store to support the exchange. Yeah. All we've got in that store are keys and hashes, and those hashes don't support smart decisions. So I can spot a delta, but I can't work out which side is ahead. Yeah, so I've got to do some crude process to do the repair. And if I want to synchronize between two different clusters, those clusters have to be partitioned identically. So all our AAE trees are based on the partition and the nval, so the number of replicas. So for every combination of preflist and nval, we have to have a separate hash tree. But that means that on the other cluster, we have to have the same combination of preflists and nvals. Okay, so we need to align those two things. so there was a kind of feature released in React to do that, to say if you've got your two clusters aligned, we can do that comparison. And so we have one system in production that used that feature rather than the key listing. And it was great when it worked. When it worked, it was way, way faster than key listing. It took a few minutes to do a comparison. Unfortunately, sometimes it didn't work, and when it didn't work, it brought the cluster down. And so that wasn't very good for our availability guarantee. So inter-cluster synchronization in the current implementation didn't work very well, and it mainly failed because it didn't handle the situation when key stores were being rebuilt and AAE was only partially available. And there's no flexibility about this. We've produced a tree about everything that's in the bucket. But what if we only want to replicate part of the bucket and we want to compare that with some other data store that's partitioned the data differently? There's nothing we can do about that. So we've been trying to work out how we can change and improve this process. So the first thing we looked at is when we're calculating the segment hash by combining all the keys and hash values for that particular segment, how is that combined in a Merkle tree? And in a Merkle tree, what it does, it takes an ordered list of those keys and hashes, and it hashes that ordered list. Yeah. So in order to produce that hash, you need to know everything in there. And so we asked the question, well, why couldn't we just take all the keys and hashes, hash separately, and XOR them together? Yeah. And the answer is there's a really good reason why you can't do that. It doesn't preserve ordering. Yeah, and there are some cryptographic weaknesses that if you're relying on this to be tamper-proof to third parties and this kind of stuff, where that would fail. But we looked at those reasons and said, well, actually, they don't count for us. Yeah, we've already, we don't care that whether the data's stored in the same order on the two places. That ordering's not important. And also, we're using this to exchange between two clusters where we're going to exchange the data anyway. So we've already got a secure channel for exchanging the data. We already trust the two actors involved in the exchange, so that is important. So we said, well, let's try thinking about using the XOR instead. And if we use the XOR in Riak, before we make an update to a database, we're always reading before we write. So we're reading to check that dotted version vector to making sure we're not going to overwrite newer data. Because we're reading before we write, we've got the old dotted version vector, which is going to be the basis for the hash. We've got the new dotted version vector, which is going to be the basis for the new hash. So we've got the base of the old hash, the base of the new hash, and we got the key. So because of the XORing, we can now create a delta. Simply XORing the old key and hash removes it, and XORing the new key and hash brings the new one back in. So we can make a change to a dirty segment without reading all the old keys and hashes in that segment. So we make that process of updating the tree much better. We can also fold across a store and incrementally build a tree. So previously, if we wanted to build a tree with a fold across the store, we've got to fold across the store first and build a full list of keys and hashes by segment, and then we can build the tree from that. Now we can fold across the store, updating each segment in turn as we go, as we see changes to that segment. So we can incrementally build a tree through a fold. And if we've got two vNodes and that have produced a tree, and we can merge now, we can XOR those two trees together. And when we XOR those two trees together, we get the combination of data represented in those two vNodes. Yeah. So in theory now we can have a database that's partitioned one way and a database that's partitioned in a different way, and we can build trees for the individual partitions on both those two databases, and we can now merge those together and provide a cluster-wide view of the store from one side and a cluster-wide view of the store from the other side that should match regardless of the different partitions, the different partitioning strategies that are used between the two stores. The other thing we got as well is that when our actual vNode stores that are storing the data, so the actual raw stores of the data, we're often using LSM trees for that, or we're using other types of stores. that are going to use some kind of hash of the key to accelerate access to that. So when we're using a log structured merge tree, we're using a hash of the keys in Bloom filters to make sure we don't needlessly look in every layer on the way down before we find our record. So we said, right, so we're using multiple hashes of the keys in Bloom filters here for space efficiency. And we asked the question, well, does that space efficiency really matter? What if we just had a single hash of the key? Yeah, so that would be less space efficient, or we'd have a higher false positive rate, or we could use something like rice encoding to actually get space efficiency back with a single hash of the key. And if we had a single hash of the key, we could make that hash of the key the same hash that's producing the segment ID. So the thing that allows us to quickly rule out checking levels if we check down the log structure merge tree and not open blocks unnecessarily, we could use that in a fold across the tree that was in key order. We could pass in a set of segment ID. So I want to fold across the tree, but skip any blocks that have got these that don't have these segments in. Yeah, and if we're only looking for 10 out of a million segments, we may be able to, even with a reasonable false positive ratio, skip across 99% of the blocks and actually fold across that tree by segment fast, even though the LSM database is actually key ordered. We can do a segment accelerated fold. Okay, so what this means is that if we have a vnode store that's got that segment acceleration into it, but is sat in its native key order state, we can still use it for those mismatched segments for returning the keys and clocks or keys and hashes. And because of that, we no longer need a separate parallel key store. And if we have a vnode store that doesn't support that, we still need a parallel key store. But this parallel key store, if we use an LSM tree that's got this segment-based acceleration, we can still have it in key order, and we can therefore reuse that key store for other purposes. Yeah, so we may be able to do other folds across there that may have other value. So this is the essence. This is the changes that we built into the KVINDEX TICTAC tree process that's part of what we're building here. And so there are the key actors in the TICTAC tree library is that we have an AE controller that in this case, in the Riak case, it's plugged into a Riak KV vnode, but it could be plugged into some other data service. And that controller receives the updates. It has a tree cache for every partition and enval that it's interested in. So a Merkle tree with just the hashes kept in memory. It goes and makes the delta change in the appropriate tree cache when it gets a change. It then has another process called an AE exchange that sits outside that. We can pass into that exchange a blue list and a pink list. The blue list is a list of controllers and partitions that have that provide one view of the database. A pink list is a list of controllers and partitions that provide another view where those two views should match. Yeah, so there could be two coverage plans in Riak, or there could just be two single partitions that should compare. So we pass that blue list to the pink list to the exchange, and the exchange says, okay, go fetch the roots, go compare the roots, go check if there's any differences to see if those are still the same. Go find the different branch IDs, go find the different segment IDs. And then at the end it says, I've got a set of differences in segment IDs. It goes to all the controllers, go return me the keys and dotted version vectors that are associated with those segment IDs. If we're running in native mode, in the top case, then we just go and talk back to the native backend and run the segment accelerated query and get those keys and clocks. If we're running parallel mode, we go talk to the parallel key store and we can return that information. So what new anti-entropy features does that give us? Well, it means that we can do more frequent checking because we don't have dirty segments anymore, so everything's always cached. So we can check more frequently, and that makes it much cheaper to double check as well. So we end up dealing with less false positives. We can actually, where we're running parallel stores, we can actually, because of the ability to fold across the store and incrementally build a tree, we can actually validate that a tree from a store is right rather than having to rebuild it. So we can spend less time with stores unavailable. We can now do low-cost full sync because we don't have to worry about this rebuild phase. It's always on, and we can merge the trees. So not only can we full sync, we can full sync across different partition clusters that have different partition sizes, and that answers a key problem in Riak, because Riak, you partition at design time your database up into some factor of 2 number of vnodes. So we choose 128. And there's no real way, no real supported way of resizing that ring to say if you decide you need to go to 256. Well, now we can actually set up a new cluster, set that to new ring size, and efficiently sync between those 2 clusters and confirm they're still the same before failing over to them. We can also compare between 2 different clusters with different end vals, which is useful for backup, which is a kind of a dirty word in Riak, but we can now back up an n equals 3 cluster to an n equals 1 cluster and check they're in sync using AAE full sync. And the other thing is potentially we could compare to other databases. So there's only really in Riak one database which people regularly compare to, and that's the Solar database, because the integration between Riak and Solar had to be written tightly coupled around this AAE store. So they had to make sure that the layout of Solar had the same amount of partitions and used the same value, so they could do these comparisons. So you could only really compare with a database that Basho had done the work to build the comparison into. But if we can compare with a database, if let's say we're comparing, one bucket with a Postgres database, as long as we can set up some kind of table in that Postgres database of keys and clocks and fold over those keys and clocks and produce a tree, we can compare that Postgres database with our Riak database for that bucket. And we can also, because we can now just run a fold and build a tree, we can fold over just that one bucket to produce the Riak side of that. So it gives lots of interesting new features. We've done some volume testing on it. So this is running a volume test over 24 hours, and this covers, this is on the sort of NHS hardware with the NHS workload, and this covers the bit between having, I think, 200 million updates, and 200 million transactions and 400 million transactions. The bottom blue line is current Riak running the level DB backend. The next line up is with active anti-entropy enabled. The next line up is running the new level ed backend, which is going to be in Riak 3.0 with active anti-entropy enabled. And the green and the yellow lines, which are very hard to tell apart, that's running Riak with level ed with either the new anti-entropy or no anti-entropy. Yeah. And what we found was a less than 0.1% difference in throughput in turning on anti-entropy as compared to a 4.5% difference they were getting before. So we do seem to have gone some way in terms of making this more efficient. And also what we found is actually, we managed to put some logging in, and we found that generally speaking, the good news is exchanges show that things are in sync. Yeah, so 92.5% of our exchanges got to the root compare stage when we just compared the roots and found that they matched. And the other 7.5%, they just went back and double checked the root and found that they now matched. Yeah, and nothing actually had to go beyond that. So that's the kind of idea that we came up with, and that's what we're now implementing in 3.0. I think it's worth mentioning that there is a potentially better idea out there, and because academia has been working on this problem, and some people have come up with this idea of dotted DB, of a way of taking the dotted version vector concept and doing things at a more vnode level to allow anti-entropy without Merkle trees, and as it says there, it also allows for deletes without tombstones. And this is a really interesting idea, and I think if we were building from scratch, we may have looked much more closely at this. As we were, because we were building from something that already had anti-entropy, it was easier for us to drop in an additional anti-entropy feature rather than having to change the way the vnodes worked fundamentally. And also, the .db paper at the moment assumes that data is never lost from disk, yeah, and we don't want to make that assumption. And there are probably things you could do to deal with that assumption, but we made the decision that it would be easier for us to move forward with writing our new anti-entropy library. But if you're interested in that area, that is really, really interesting research, and it's a really interesting paper, and I fully recommend you read it. Related work to what we've been doing on, I mentioned level ed. So I came and talked here last year about the level ed database, which is a pure Erlang log structured merge tree key value store that we're now getting ready to be a fully fledged vNode backend for Riak. And this allows us to move away from level DB. And the main reason for moving away from level DB is to really address the complexity of maintaining the level DB code. It's moved a long way away from the original Google level DB. It's a very specific Basho thing now. The guy that wrote it isn't around. Basho isn't around. It's hard for us to maintain and manage that now. So it's much easier for us to have a pure Erlang log structure merge tree. And we are getting some better results in performance out of that. And that's not, I'm afraid, because Erlang's better than stuff written in C++ for performance reasons. That's simply because we made some design decisions that were much more suited to the NHS's environment. So the level-ed database is much more tuned for having larger object sizes than level DB, and it fundamentally supports the concept of head requests at lower cost than get requests. And in Riak, if you can use head requests in your backend, you can make some of the things more efficient, because rather than getting things from 3 places, you get something from 1 place and get head requests from the other places and just do the comparison, and only do the get if you find the comparison needs is required. We've done some work in Riak on what we call core node worker pool. So currently, if you want to set up a worker in Riak, you have a pool of workers per vNode. So you've got typically 15 vNodes on each node, and you've got a pool of 10 workers, so you've got 150 workers there. So that's really good for maxing out your Riak, but often we don't want to max out Riak with work that's done through folds. We want to control it. So we have this thing called core node worker pool, where you have a very small pool of workers that's per node rather than per vNode. We're also doing some work on coverage fold. So MapReduce is a bit of a dirty feature in the original Riak. There are all kinds of side effects of using it. And what we're trying to do now with coverage fold is have folds that use that core node worker pool, and then can simply fold over ranges of keys in an efficient and controlled way. So you don't get fast results out of multi-key requests, but you can get controlled results that don't have an impact on the rest of your store. And you can pass generic functions into those coverage folds and generic accumulators as well. So it's not just about adding to lists. And there's a thing called Rabble as well. So the current real-time replication in Riak does all kinds of bespoke queuing and bespoke deep access to TCP protocols and this kind of stuff. And so Russell Brown has got a prototype of replacing that with something that builds on top of RabbitMQ and allows RabbitMQ to do all of that low-level stuff, and then we just use the queue feature of that. And so all of those things we're hoping to get into Riak 3.0. So that's it from me. I've just about squeezed into 40 minutes. The presentation's on GitHub. All the other stuff is on GitHub. And thank you very much.